Welcome you all to this video lecture. Today we actually go through formula for root locus sketching, and this is very important. So I just wrote the formulas that we need before sketching an accurate root locus. So in that case, so first formula is the asymptotes. So if you remember, last time we discussed what are asymptotes. Asymptotes tell us about the branches of root locus that goes to infinity. So there are 2 points in asymptotes. One is the location of the asymptotes and the angle at which they departed towards the infinity in S-plane. Now look here. So asymptotes, we have the location that is calculated by entering the values of the location of the poles, that is finite poles, minus values or location on the S-plane for the real one of the zeros. If you do that and divided by number of finite pole minus zeros, this will tell you the location on the real axis where this asymptote will be go towards the infinity, and this will tell you at which angle it will go to infinity. So angle is 2i plus 1 times pi times a difference between the poles and zeros, and this I is from 0 1 plus minus 2 and so on. Okay, now the next point which is important, we required when this asymptotes go towards infinity, it can go towards the right hand side, or in sometimes our root locus didn't go infinity but it crosses the j omega axis. So we need the values where they crosses the j omega axis, the imaginary axis. So for that case we need Routh-Hurwitz criteria. So we already discussed this in previous videos. So what we do, we use the case where we have whole row becomes 0. So what we do there, actually we just calculate the values of k that makes a row 0, and then we move to going back one row to the even polynomial and then put that value of k and solve for the root that yields the frequency at j omega axis. So this is the second part. So again I told you, first is the root asymptotes, then you have to find the j omega crossing. Now after that there's another one. Whenever you have branches departed, you must know that at root locus level at which point these branches will be departed. So for that reason you need break-in or breakout points. So break-in points means that if branches are coming into that known as break-in point. For example, I just explain here, if you have a zeros, we know that if there are two zeros and we know that root locus will finish at the 0, so we have to find this point from where a particular branch break in. So for zeros this is break in. Okay, so we call it break in. So if we have a poles and we know that root locus always departed from the pole, so in that case we have to find the location at which location it will be go in any direction. Okay, so in that case this is known as breakout. So this is known as breakout. So that's why we have to look for both break-in and breakout points. All right, now how we do that, we just have to write the characteristic equation. So if you remember, characteristic equation is delta of s is equal to 1 plus k g of s h of s equal to 0. That implies that we have to calculate k is equal to minus 1 over g of. Now for finding these points, what we do, we have to take the derivative of k with respect to s and put equal to 0. So we have to solve this equation, that is derivative of k with respect to s equal to 0. Now we get the values of s from this equation, and that give us the break-in and breakout point. Now the next formula that we really need to solve for accurate sketching of the root locus is known as angle of departure and angle of arrival. Now I told you last time, so departure means that if you have some poles and we want to know in which direction this angle will be, so in that case this is known as angle of departure. In case of zeros is known as angle of arrival. For example, to clarify this concept, let's see we have a pole here, 0 here. Okay, So we have to know that if they are in geomag axis like this, and there's some zero here or some pole here, okay, so we must know that how this zero will terminate toward this this pole will terminate root locus on this zero, either in this direction or in this direction. So this is question mark that will be answered by this angle of departure, that tell us that either we have to use for example, if I calculate the angle, use this angle or use that angle. So this is our question. If we are looking for pole is known as angle of departure. For zero we call it arrival. So this is the basic idea that we have to look. So for that case, we know that how we calculate the angles. We have to calculate the angle of zeros minus angle the poles and put equal to 2i plus 180 degree, and we solve this. So how we do that? We assume that there's a small circle. If I draw here, for example, if we have a pole, we assume a small circle and assume that this circle has some angle, for example phi d for departure. If we have a zero, we say a for arrival. So now from this angle, if we have different poles and zeros, we just draw a line and just try to calculate the angle. Okay, draw a line, just try to calculate the angle, and from this angle we put the values here. If it is 0, we put the 0 angle here. For pole, we minus the pole angle and put equal to 180 degree and solve it. We can easily calculate the angle of departure and arrival. Now I again go through it. So the formula is very simple. First one is asymptote, second is j omega crossing, for which we need root locus routes table, then break in breakout point, and the last one is angle of departure and angle of arrival. Now to look at this in detail, let's do an example. Example is I just wrote example in terms of k, g of s, h of s. So because this is the basic information that we need to draw the root locus. So from here we know that there's no zero, only poles. So one pole is at origin. I draw it in the S plan. So this is my S plan. So to clarify it, this is my S plan. All right, so first pole I draw it at 0 due to this, then -1, then -2. So this is the first step. Now from here we know that how many poles we have: 1 2 3. So n is 3, number of poles 0 is 0, so the difference is 3. So this means that there are 3 zeros that are not available here, but they are at the infinity. Now where at the infinity we need the information about the asymptotes. So first one is number of asymptotes. So we know that number of asymptotes is the difference between poles and zeros. So n minus m is 3. Now location of asymptotes, how we do it? Now what is location of first pole? Is 0, we put 0 here. Then minus, what is the location of second pole? -1. Third pole -2. Because we already discussed this formula, finite poles minus finite zero difference. Look here, location of poles 0, -1, -2 divided by 3 minus 0, there's no 0, so I put minus here, equal to -1. So -1, this is the point where you have to draw the asymptotes, but the question is at which angle. So for angle we have to use the second formula that gives 2i plus 1 pi divided by finite minus finite 0. So before this we can also know that root locus exists between these poles, because if we look in this direction, the number of poles and 0 is 0, which is even, so there will be no root locus till this pole. After that number is odd, so we have root locus till the next pole come. After next pole again this number becomes even, so there's no root locus here. Again there's a root locus. So after drawing this, we can apply this formula of the angle here, and from this formula we assume I equal to 0, and when we put 0 here, because how many angle we need? 3, so we start from 0 1 2. Okay, so this is the formula that we have to implement. Okay, there are three differences, so we have to go up to 2. So for 0 1 2, we put the formula 0 here, it becomes 60 degree, 1 here it becomes 180 degree, 2 here it becomes 300 degree. So you can solve it. This is the one way of doing it. The other way, I told you in freehand sketching, that you have to make a circle here. So this is the circle. So we have to divide it into different we can have to divide into 3 parts. So first one is that we can cut it in this direction. Second one tell us that we can cut in that direction, either we can cut in that direction. So these are possibilities. Now if this is my real axis, so look here, this becomes 60 degree, this becomes 180 degree, and this becomes 300 degree. All right, because this is minus 60. Okay, now again this one, if I look here, this becomes um, so this is 120 degree, 120 and 60, 60 plus 120, 120 means it's 240 degree. Okay, again this becomes again 120, so 120, if I add it to 120 is 360 degrees. So this is another possibility. Now from these possibilities, we have to look for the real axis. So if you look here, real axis, this tell us about that one will be go in this direction. So if we look at we are because there's nothing going infinite to the right side, so this is not selected, though this is selected because here left side is going toward infinity. Look here, so we from easily know that this is 60, 180 and 300, so we get the same result here from the formula. Now the next one is we have to sketch the root locus. So sorry, asymptotes. Now here this is the -1, alpha is equal to -1. We draw 60 degree line, we draw 300 degree line, we draw 180 degree line. So up till now we know the root locus at real axis and asymptotes. Now next question is, because they have to follow this line, so we know where they cross the j omega axis and also at which point they will go in which direction. Okay, so for that case we will move to next part, and which is j omega crossing. So for j omega crossing we need delta of s, so I write the delta of s here. Now after that we know that how to write the routes table. Now I make the routes table. I put 1 here, I put 2 here from here, then I put 3 here and k. Now after this line I solve this using this. I take the determinant of 132k minus divided by 3 by this number, so it becomes k minus 6. I put 6 minus k divided by 3. Now after that I take this and move to this. There's nothing, I put 0 0. 1 minus 3, I solve it, becomes 0, so I put 0 here. Now I move to this one, again I do the same thing. 3 6 minus k, 3 k 0. When I solve this, this becomes k, and again this becomes 0. So this you can solve it. Just pause the video and solve it by yourself, so that you will revise your routes table and also know. Now for j omega crossing, what we have to do, we have to make this whole row 0. How we do that? We just make this equal to 0. So I put this value equal to 0. From here I calculate the value of k. Now when I put the k, this row whole becomes 0. Now I move to next row, above row, which is even row, that is s square. Now I have to write the polynomial here. Now move one row above and write polynomial. This becomes 3s square plus k equal to 0. Now I put this value of k here. So from here it becomes 3s square plus 6 equal to 0. Now s square is equal to -2. From here we know that the location from where j omega crossing is done by the root locus, that is plus minus under root 2j. Okay, now the next point is from where on real axis this point will originated by the root locus. So for that case we have to calculate break-in breakout point. How we do that? Again the same characteristic equation I write and I calculate for k. Okay, so pardon me, there's a plus here. Okay, now after that, when I calculate the k, now I have a minus sign here in this side. Now I have to solve this equation because we already discussed this thing in the formula, how we calculate the break-in point. We have to solve this equation. Now here I do the same thing. I put this equal to 0. From here, when I solve it, put equal to 0, it becomes 3s square plus 6x plus 2 equal to 0. Now I calculate the roots of this equation. There are two roots. It becomes minus 1 plus minus 0.5773. Now it becomes minus 1.5773 and s equal to minus 0.423. Now to choose which is the acceptable, we have to move back to our original root locus. Look here, root locus only exists when it is less than minus 1 and greater than minus 2. Now here, if I look the value, one value is not satisfying the real axis plot. It is here, so there is no root locus here because it is for negative k, so that's why we get these values. Now we are looking for k positive. Okay, here we are considering that the value of k is greater than 0. This is also true but less than 0. Okay, so for greater than 0, we just look at the real axis. Now we come to know that the breakout point, because these are poles, so there must be a breakout point that goes to j omega axis. Crossing here is under root 2j, okay, and minus under. Now from here we know that this point is minus 0.423. okay, now we find this point, we find j omega crossing. Now it's time to just sketch the whole root locus. So look here, this is my 0, this is my minus 1, this minus 2, this is my j omega asymptotes angles. Okay, now here this is the breakout point, which is minus 0.423, which I calculate now. Now it will cross this point at plus under root 2j and minus under root 2j. So this is whole my root locus. Okay, root locus plot. Now one thing we already discussed was the last one is angle of departure. We discussed that this last one, angle of departure. Now what about here? Actually we don't need to do the calculation of angle of departure here, because we don't have any poles at 0 that lies in j omega axis in coordinates. They are on the real axis, so we don't need it, but we do it for completeness so that you understand the whole idea. So I do it here. Now angle of departure, how I do it, I make a small circle around the pole and call it as a departure angle d1. Similarly for this d2, d3. So for when I do for d1, I just calculate the angle from this pole to this pole. Now angle from this pole to this pole, when I move to this pole, it take me 180 degree to do that. Similarly, when I move to this pole, again 180 degrees. So we have a departure angle minus plus 180 degree, plus 180 degree, minus angle of 0. There's no 0, so we have to apply this formula, that is angle of poles minus angle of zeros. Okay, now equal to 180 degree. So I put the angle of for this pole to calculate the angle of departure. I put d1 plus 180 degree plus 1 equal 180 degree. 180 degree cancel out, d1 becomes 180 degree. So the angle, if you look here, so it will, the root locus lie at 180 degree. Now again for next one, for this one, look here, when I move in this direction, so there's no angle I required to move in this direction, but for this direction I need 180 degree. Okay, so for that case it becomes 180 degree 0 and again 0 degree, again 180. So this is the way we calculate the angle of departure. So this is the whole example where angle of departure and arrival are not required because they are on the real axis, and we easily calculate angle of departures, a whole root locus, sketch it very accurately. You can confirm it using the MATLAB. So I will stop here and I will do another example based on this formula so that I will complete this. Now this root locus, how it help us to design a controller. For example, when we discuss in next phase, we know that if you remember we have some specification of design. That specification, if you remember, we have curved something like this that tell us that our closed loop pole must be lie in this direction. In case we if you remember, we discussed this as a zeta, that is overshoot. This is as a rise time, then we have a settling time. So this design is not satisfying that. So we have to choose values of k that satisfy these constraints. So from where we can do it, but if we can't, then we have to add some dynamics or zeros here so that we can get this result. Okay, so before designing the controller, we must know that how this root locus is sensitive towards the pole location and zero location, so that we understand which controller we require to design, or we can work out only with a gain controller. So thank you. I will stop here. We'll continue in next video. Thank you.